In this video, we are going to continue the topic of graphs by looking at distance-time graphs. This probably makes a bit more sense to be talking about distance-time graphs in this topic because when you're talking about direct and inverse proportion, we end up not really looking at many graphs. The reason why is because they're kind of setting up for graphs. Well, with this part of the topic, it is immediately looking at a graph. In fact, it's all it is. It's just analysing graphs. But the key with the distance-time graphs is that the questions will have axes instead of x and y. We tend to have time and distance. Okay, that's why they're called distance-time graphs. Most of the time, distance is going to be the y-axis and time will be the x-axis. I'll explain why in a little bit. There's not much to really talk about in regards to the theory, but you'll see what I mean when we start looking at an example. So for example 1, the distance time graph shows the journey of a cyclist on a training ride. The first part of the question asks, what is the total distance covered? Okay, so for this we are looking at each leg of the journey. Okay, so you'll see here the cyclist starts and then they go 10 kilometres and then from 10 kilometres they go further until they get to 50 kilometres. So to get to here, they've gone 50 kilometres. So I'm going to write that down. So they've gone, they've gone 50 kilometres. But then you can see they've come back here, they've done something, and then they've come back to E. And so they've gone from 50 kilometres to 0. So they've gone another 50 kilometres. Essentially, they've returned back home or they're back to their starting point. So I can add another 50 kilometres. So the total distance travelled is 100 kilometres altogether, which is quite far. But you'll notice it took them 6 hours to do that. So it wasn't like they just went out for a quick ride. That was a whole day thing. Part B says the cyclist's speed increases at B. How is this shown on the graph? Okay, so you can see that they're travelling along here, and then now we've got a steeper incline, and that's how we know, because the graph is steeper. Now, the reason why the distance is here and the time is here is because the formula for speed, which we actually did in one of the 5 questions, speed is equal to distance over time. Okay, so that's very similar to the gradient, which is rise over run. Okay, so because distance is the rise and time is the run, it has to be distance over time. It has to be the distance on top because it is the rise. It helps us when determining things like this, part B. So you can see we've got a shallow gradient and then we have a steeper gradient. So the speed increases because the gradient has increased, which means that the speed has increased. So that's all we need to write. The graph is steeper. So speed increases. Okay, so it all comes back to this, rise over run. Part C says to calculate the speed of the cyclist from B to C and then again from D to E. So we're going to use this formula, speed equals distance over time. So for the speed for B to C, the distance travelled is from 10 to 50, so that's a total of 40 kilometres travelled. And the time was from 2 to 3, okay? So 2 to 3 hours, that's 2 hours total. Oh, sorry, 1 to 3, which is 2 hours, yes. So he's travelling 20 kilometres per hour. By the way, a way to remember speed equals distance over time, you'll see here, this is a fraction with the distance of kilometres over time in hours. So it's the same thing there just to help us remember. Okay, and then we'll do the same from D to E. And I'll move the graph just a little bit because it does line up with these boxes. So you can see now for D to E, D is like halfway between 3 and 4, so it's 3.5 hours, and then E is 6. Okay, so one thing that might be easier, instead of going straight into figuring out thing, is to actually draw on the graph. So I'm looking at this here. So the rise here was that's 50, because it went from 0 to 50, and then this one is going to be 1, 2.5. So I'll just write 2.5. So the speed from D to E is going to be 50 over 2.5. If you type that into the calculator, you'll get 20 kilometers an hour. So that's interesting, and it makes sense why that would be the same speed, because these look like the same gradient, but just one is negative, and that's because they're going backwards, that's all. But the speed is actually the same. Now part D says, when was the cyclist stationary? So let's consider this graph, and it's basically telling a story. So starting at 0, they go at a speed, and then they speed up, and then something happens, and then they speed up again, but going home, going backwards, effectively. So the cyclist is stationary here. They've taken a break for about half an hour because they haven't travelled any distance. So they haven't gone up or down, but time has passed. Okay, so that's when the cyclist is stationary. So we can just say C to D. They stopped for 30 minutes or half an hour. It's up to you how you write that. And if you want a reason, because the graph is flat. Now, if you wanted to back that up with a mathematical response, like something like this, speed is equal to distance over time. Well, they've travelled 0 kilometres over 30 minutes. So yeah, that would still result in a speed of 0 kilometres per hour. So that means that they're stopped. The last thing that we want to look at is different distance time graphs with variable speed. Now, the graph that I just showed you is all well and good, but it's assuming that basically that cyclist is a machine, because realistically, you don't go from not moving to going 10 kilometres an hour. You have to build up to that speed. So that's what this example is about. So example 2 says to describe the journey represented by each distance time graph. So the first step is I'm going to get a pen, and I'm going to write what's actually happening for each of these graphs. So, and I'm going to label them, kind of like how the cyclist was labelled. So something happens at A, something happens here, and something happens here. There's a bit more going on, but I'm just going to use that so I can help describe what I'm talking about. So I can say the person, we're assuming it's a person here, but it could be a dog or who knows. The person starts moving at a constant speed. And I'm just going to write in brackets A. So you can see here that because it's basically a straight line, that means they're going at a constant speed. But then they pick up speed. And we know that because it's a steeper curve, steeper gradient. They speed up at B. So you can see, so we're going constant, then they speed up because we're going steeper, but then you can see it starts to flatten out again before slowing down at C. I'm going to say to a stop. The reason why I'm saying it's to a stop is because it gets to this point and it's basically flat. So they must stop somewhere. I'm not saying it's a stop because the curve finishes, because the curve could keep on going, but it's because it's flattened out. Okay, we're going to use that same approach, but we're going to do it for this next curve. And there's a bit more going on here. We might have a few more letters. So we've got A, so we'll start off there. And we've got B, C, and then D at the end. So we can see with this curve, the person isn't home, say. The person is leaving. They're going from somewhere back somewhere else, okay? At a high speed. And we know that because of how sharp this gradient is. They then stop at B. Okay, because we've got a flat line here. They're not moving. They're not changing distance. The person then speeds up. At C. Then slows down to D. Okay, and the reason why I know that they're slowing down is because it's the speed, but then it starts to slow, like the curve it reduces in steepness. Okay, so that's for B. We've only got one more to do. You can see that there's a bit of intuition with this. It's a bit more, this is probably as close to English as we will get in maths for at least a while, because you are essentially describing a story based on an image, kind of like a stimulus. So that is interesting. For C, there's only two really interesting things happening. What's happening at the beginning and then what's happening at the end, really. So I'm going to say the person leaves home. So you can kind of like create a story for this. Leaves home and slowly increases speed. At A. You'll notice throughout these questions I don't always mention every letter, but the letters are more for us, not so necessarily, and sometimes to direct the person, but it's not always essential. So they start off slowly, increasing speed. I'll do a comma there, until they reach a constant speed at B. Because you can see, so they're going from relatively flat to steeper, and then it just goes straight up steep. And it doesn't change, it's not curvy. That means it's a constant speed because it's not wavering, it's just constantly going the same speed. We can draw a triangle type of thing, and that's the rise over run. Constant speed there. Where here it's constantly changing because we've got all these different curves. Okay, so that's basically it. I'll just quickly recap. So there's two main things you can be asked. You can be asked to analyse a distance time graph. You can be asked to analyse a distance time graph with a variable speed, which is where it gets curvy. And then the other time is actually if sometimes you might need to draw a distance time graph based on a story. So kind of like the opposite of what's going on here. That is a bit harder. And the reason why we're not doing an example for it is because as you go through maths into the HSC, you don't really get asked to do that very often. It's more doing it this way. So that's why we're only looking at these two examples. Anyway, please move on to the textbook questions and